Okay, this is called the logistic equation. If you graph a logistic equation, it kind of looks like this, where it starts off small, increases pretty fast here in the middle, and then sort of levels off here at the end, according to what's called the limit. With the logistic equation, today we're just going to talk about what the form looks like and how you set up the equation, and then tomorrow we'll talk about the word problems with it. Some word problems that relate to the logistic equation are like maybe there's a rumor that's spread at school, and the question would be how long it would take till the whole school knows the rumor, or when the rumor is increasing the fastest would be another question that they would ask. These are very similar to those differential equations that we did about the animals dying. It's kind of similar to that, except the equation is a different form. Okay, so I took a picture for you to show you where it comes from. Basically what happens is this is the form of a differential equation that is logistic equation. That's important for you to memorize. All right, what's going on from here is I'm solving to try to get p by itself. It involves partial fractions and it involves some other manipulation. If you're interested, I'll be glad to talk to you about that. The important part is that this is the equation that's equal to p. So if I take that differential equation that's in purple and I solve it, I end up with this equation. So you need to memorize that the differential equation Kp times 1 minus p over L, if you solve that, you would get p equals L over 1 plus ae to the negative kt. One other important information you need to know is this right here, that a equals L minus P0 over P0. P0 stands for the initial population or the initial amount in the problem, and so that's another thing that you will need. Now, some other important information. If I want to find the limit of this logistic equation, that's what is going on down here. And I'll rewrite it just in case you can't see it. So the limit of the differential equation is L. That's what the L stands for in the equation. And this down here talks about when the maximum would occur. In the rumor problem, that's whenever the rumor is spreading the fastest. Well, since the graph of it looks kind of like that, it would be increasing the fastest in the middle. Well, if this is L, because that's what it's approaching, then this has to be L over 2. So we call that the maximum peak, and that equals L over 2. If I wanted to find the time when it reached the maximum peak, I would be looking for t, and you would use this red equation here, plug in everything that you know, and then you would solve for t. Okay, so let's look at some examples. Okay, so this is a logistic equation. It's written in that form I was showing you earlier. And what we want to do is we want to rewrite it so that it's p equals something. And we don't want to have to go through the process every time because that's pretty difficult. They just expect for you to know the form. So this is in the form. The original equation had a k and then a p and then a 1 and p over L. So the equation we're looking for is a over 1 plus, I'm sorry, that's not right. It's supposed to be a L. L over 1 plus ae to the negative kt. Okay, so if I look at how it's set up, So the L is 100. The A we don't know. The K is 0.4, so you put negative 0.4 T. And that's all you do. Just rewriting it, at least at first. Okay, here's another example. The only difference on this example is that this doesn't say P over something. It has the 1, it has the P, and the number in front, but it doesn't say 1 over, so just put that in your calculator, change it to a fraction, and you should get 1 over 2,500, so that's P over 2,500. So now, if I rewrite it, P equals the limit, which is 2,500, over 1 plus A, E, negative K is that 0.35, T. Okay, next example. Now this example, there's several things wrong with it as far as the form looks, but also it gives us an initial value. So on this problem, what we're going to look for is when the maximum is occurring. We're going to find the maximum peak and then find the time of the maximum. So first thing we have to do, though, is we have to make that equation into the correct form. We need this to say a 1, so we're going to factor out a 10. So we're going to have 10p times 1 minus, and so in your calculator, you're just going to do 0.1 divided by 10, or if you know what that is, you don't have to use calculator, obviously. And then change it to a fraction because we want the limit to be on the bottom. So you get 1 over 100, or p over 100. So now it's in the correct form. So let's write it as the equation A equals 100 over 1 plus A E to the negative 10t. Now, because we know this p of 0, that's where I told you had to remember that A was L minus P0 over P0. So L is 100, P0 is 20, and then divide by 20. So we get that A is 4. So then we can rewrite that equation. Now, the question for us to figure out is what the maximum peak is and when that occurs. So remember, logistic looks like this right here. So we're trying to find that x and y value pretty much. The y value is always half of the limit. So the limit is 100, so I'm setting this equal to 50. And then I'm going to solve for t. So 50 is the maximum peak. Because that's whenever it's growing the fastest. Alright, so I cross multiply. Divide by 50. Subtract 1. Divide by 4. Take the natural log on both sides. Divide by negative 10. And I get 0.138. So that means that whatever this is talking about is increasing the fastest at t equals 0.138. Okay, here's another one. We also know a P0 here. I forgot to write that in. We're going to do the same kind of problem. Go ahead and find that maximum just to make sure we got it. Now, before we can continue, though, I need to make this look like the correct equation. I know that it needs to be something times 1 minus something, so I want that to be a 1, so I'm going to factor out the 0.5p. And then I'm going to divide the 0.0002 divided by 0.5 and change it to a fraction. You get 1 over 2,500. That's p squared. I'm factoring out a p, so really the top is just a p. So So that will give me the equation A equals, that's not correct, P equals 2,500 for the limit over 1 plus A e to the negative 0.5 t. And I know that A is the limit minus P0 over P0. And I don't know where that came from, but that is 4. So then, if I want to find where the maximum occurs, plug in that 4. I know that the maximum increase in the fastest where L over 2 is, and L over 2 is 1250. So I set that equation equal to 1250. Put that over 1, cross multiply if you need to. So that's 1250 times 1 plus 4e to the negative 0.5t equals 2,500. Divide by 1250. Subtract 1. Divide by 4. Take the natural log and divide. So natural log of 1/4 divided by negative 0.5. And you get 2.772. And so this one is increasing the fastest at t equals 2.772. And A happened to be 4 here, and in the last problem, that won't always work out that way. It just happened to the way that I set it up. Okay, so here's your try problems. Number 1 and number 2, I just want to know what P equals. Just rewrite those two in the correct form for logistic. On number 3, I want you to rewrite it, figure out what P is, and then find out what the time where it would be increasing the fastest would be, the way that we did the last 2 examples.